Now we're going to talk about the process of creating regular grammars. We've looked at two mechanisms that we can use to specify regular languages. One is the deterministic finite automata, then we looked at non-deterministic finite automata, and now we're going to look at regular grammars. Now, this is not going to be substantially different from what you've seen before, but the mechanisms are different enough that you need to familiarize yourself with them. So if we have a finite state machine, it doesn't matter whether the finite state machine is a deterministic finite automaton or a non-deterministic finite automaton. We can create a grammar out of the state machine, a valid grammar out of the state machine, by following the procedure that we talked about earlier. Here we have at the bottom of the slide a finite state machine that recognizes 1100 at the end of the string, and it's non-deterministic. We'll create the grammar exactly as we would before. We'll start with state A and take all the transitions out of state A and turn them into productions. The arc that goes from A to B, we turn into the production A goes to 1B. It's normally how I pronounce productions, and I want to remind you of that. For the self loop, I end up with two productions because the self loop is actually two loops that have been combined into one. I have A goes to 1A, A goes to 0A. That takes care of the self loop. Then I go to state B. It only has one arc coming out of it, but that's okay because grammars do not have to be deterministic. And so I have B goes to 1C, C goes to 0D, D goes to 0E, and E goes to epsilon. And that gives me a grammar that will generate all strings ending in 1100. The start symbol is A. Okay, it's very easy also just to start from scratch and create a regular grammar from an English description of the language. We had four types of problems that we concentrated on with deterministic and non-deterministic finite automata. And that's finding a substring in the middle of the string, a substring at the end, a substring at the beginning, and a substring by itself. And there are ways to combine these problems into more complex specifications, but as long as you know how to do each one, then you're covered here. And we also looked at and or problems and how to solve those. And let's now go through and show how this works when you're doing regular grammars. To generate a specific string, we do the following. Remember that a grammar is a generator, not an acceptor, the way finite automata are. So let's assume that we want to generate the string 11100 somewhere. It doesn't matter exactly where, but we're going to generate it somewhere. We create a new set of non-terminal symbols, one for each symbol in the string and one more for the start of the string. And so I'd end up with six. I have 5 characters in my string. I need 6 non-terminals. And we're not going to use these non-terminals anywhere else. This is for this string and for this string only. If you need lots of symbols, you can use symbols that have more than one character as long as you're clear about what's a non-terminal and what's a terminal. So we create the following productions using our 6 symbols. A goes to 1B, B goes to 1C, C goes to 1D, D goes to 0E, and E goes to 0F. This gives me a set of productions that generates that particular substring 11100. Now, depending on where I want the substring and what sort of problem I'm dealing with that involves that string, I'm going to have to add additional productions. So let's take a look at 1001 anywhere. I create the productions for the string. A goes to 1B, B goes to 0C, C goes to 0D, and D goes to 1E. I want to generate an arbitrary string at the beginning, and I can just use that first symbol A to do that. And so say A goes to 1A, A goes to 0A. That gives me an arbitrary string at the beginning. I want to generate an arbitrary string at the end. And so say E goes to 1E, E goes to 0E, just using the symbol I've already got there. And that gives me an arbitrary string at the end. And I also want to terminate the string. And I do that with an epsilon production, saying E goes to epsilon, and that gets rid of my non-terminal symbol. In this particular grammar with 1001 anywhere, A is the start symbol. Now let's just talk about arbitrary strings and termination. If you want an arbitrary string, you need a pair of productions that looks as follows. Now we only need 2 productions because we only have 2 input symbols. If I had 100 input symbols, I'd need 100 productions. Let's not do that, all right? And so here I have 2 input symbols. So I have x goes to 1x and x goes to 0x. That symbol appears, x appears 4 times, and that's the pattern you want for generating arbitrary strings. Now these could appear independently or as part of a set of productions that generate some string the way we did in the previous example. We'll show examples of doing this independently as well. And of course, strings are ended using a production like the following: x goes to epsilon. Now you can also end your string by using productions of the form x goes to 0 or x goes to 1 or x goes to some terminal symbol. If you use these types, you better make sure that you really want that terminal symbol that you're going to generate with that. So think about that carefully. In some cases, it's pretty obvious that you can use those. In other cases, if you're wondering about whether it's okay and you're a little confused about it, just use the epsilon production, because that, quite frankly, is a little bit easier. All right, so now we're talking about a substring at the end of a string, and we want 0011 at the end. So we create the productions for the substring. A goes to 0B, B goes to 0C, C goes to 1D, D goes to 1E. I put an arbitrary string at the beginning. I'm going to do this as an independent thing. Oh dear. Should say S goes to 0S, S goes to 1S. There's a typo there in the first production. S goes to 0S, S goes to 1S. S is the start symbol. And then we'll connect the 2 sets of productions together by saying S goes to A. I could have done it the way I did the previous example, but I wanted to show 2 grammar done in 2 pieces connected together with a production of the form S goes to A. And of course, I'm going to end the string. Remember that this 0011 has to appear at the end of the string, so I do not put an arbitrary string at the end. I simply say E goes to epsilon, terminating the string with that last 1. And here's a little bit more about connecting grammars. If you're creating a grammar and you have some complex specifications, you may want to do it in pieces, and then connect 2 or more pieces together using productions of the form x goes to y. Now, if you're doing this, remember to use a different set of non-terminal symbols for each piece. Don't share them. Sharing symbols between the pieces almost always causes a disaster. And the preceding example shows a grammar constructed in 2 pieces and then connected together. Now let's take a look at 5 ones at the beginning. We create the productions for the substring. Woo, 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 woo. Boy, this is a mess. A goes to 1B is what it should say. B goes to 1C. C goes to 1D. D goes to 1E. And E goes to 1F. I don't know how all those typos got in there. I apologize for that. But the symbols after the one should be B, C, D, and E, not all A's the way they appear here. A is the start symbol, and the only place it should appear is on the left of that first production. We're going to add an arbitrary string at the end using a separate piece. Z goes to 0Z, Z goes to 1Z. And then I'll connect the two. F goes to Z. And I end the string by setting Z equal to epsilon. Z goes to epsilon. All right, suppose I want 0, 1, 0 and nothing else. I create the productions for the substring. A goes to 0B, B goes to 1C, C goes to 0D. A is the start symbol. I end the string with D goes to epsilon. Very simple. Now, if we want to, we could replace the two productions, C goes to 0D and D goes to epsilon, with C goes to epsilon. Excuse me, with C goes to 0, C goes to epsilon would be a disaster. So we can take those two productions and replace them with a single production if we really want to. Doesn't really matter. Now we want to look at OR problems. We want to generate all strings that contain either 1100 or 0011 anywhere. We create the productions for the substring. A goes to 1B, B goes to 1C, C goes to 0D, D goes to 0F. That's for the first string. The second one, X goes to 0Y, Y goes to 0Z, Z goes to 1V, and V goes to 1W. Notice that I use completely different symbols for the two substrings. You have to do this. Now we're going to create a new start symbol S and hook it into the two chains. And the way we do that is S goes to A and S goes to X. We're going to join the two chains at the end using a new non-terminal Q. Say F goes to Q, W goes to Q. And we'll put arbitrary strings at the beginning and end, and then we'll end the string. So I have S goes to 0S, S goes to 1S. That gives me an arbitrary string at the beginning. I've joined the two substrings into the state Q, so if I put Q goes to 0Q, Q goes to 1Q, then I have an arbitrary string at the end, and I simply have Q goes to epsilon to terminate the string. Now let's look at an AND problem. Suppose we want to generate all strings that have both 0, 0, 0 and 1, 1, 1. I like to choose these two strings because they don't overlap. With an AND problem, you do have to account for that if the strings do overlap in some way. But I don't want to go to that trouble here, so we're not going to. So we create productions for the substrings. A goes to 0B, B goes to 0C, C goes to 0D for the first substring. Now I haven't used E yet, so E goes to 1F, F goes to 1G, G goes to 1H for the second substring. I'm not sharing symbols between those sets of productions. I hook them together and put an arbitrary string in between. Say D goes to E, and I have D goes to 0D, D goes to 1D to create the arbitrary string in between. I could do these productions with E instead of D, right? It's fairly obvious that I could. Now, that gives me 0, 0, 0 followed by 1, 1, 1. I need to have it the other way as well because 0, 0, 0 could come first. That's perfectly legal. So I create a new set of productions with an entirely new set of symbols, non-terminals. So K goes to 0L, L goes to 0M, M goes to 0N for the 0, 0, 0. Another typo here. It should be, all right, should be K goes to 1L, L goes to 1M, M goes to 1N. And then P goes to 0Q, Q goes to 0R, and R goes to 0T. I will correct these typos before I upload this this PowerPoint, and so you'll be able to refer back to it with the typos corrected. Okay, you hook them together the same way you did the first pair. All right. And I put an arbitrary string in between. Okay. Now, I create a new start state, hook it into the two chains, and create an arbitrary string at the beginning. So S goes to K, S goes to A. That hooks it into the two strings. S goes to 0S, S goes to 1S, gives me an arbitrary string at the bottom. Join the two chains into a symbol Q, and then add Q goes to 0Q, Q goes to 1Q to give me an arbitrary string at the end. Q goes to epsilon, ends the string. As I said before, I will make those corrections to this set of PowerPoints before I upload PowerPoint, so you can go over that if you want with the corrections inserted. It's time now to start an entirely new topic, that of regular expressions. That's a fairly complex subject, so I'm going to leave that, and we'll do that on Monday. We will commence looking at regular expressions on Monday. Have a nice weekend.